In section 2.4, we're going to turn our attention from looking at an entire data set to instead focusing on an individual data value. Our goal is really going to be to try to figure out how different individual data values are positioned within a distribution. So as I stated here at the beginning, we've already talked about that with an entire set of data, we can describe things like the shape, a measure of center, and a measure of spread. And again, our goal now is to figure out where are individual values located within a data set, and how do I begin to determine whether or not those individual data values would be considered rare or not rare. To try to get a sense of what I mean, take a look here at example number 1. A machine is designed to dispense paint into paint cans. I don't know, maybe you have seen paint at Menards or Home Depot or something like that. You worked at a paint store potentially, and they have these machines, they spit out maybe a little bit of dye or something like that into a paint. But imagine that the can itself is getting filled up completely with paint by this machine. And it dispenses, on average, 128 ounces. But again, that's just on average. Sometimes there might be a little bit more, sometimes it might be a little bit less, just kind of depends. Suppose that one can is found to contain 126 ounces of paint. Now, obviously, we can see that's below average. But the question that we would really be interested in posing here is there a rare amount of paint in this can? Is 126 considered rare, as in not very likely to happen? Well, I kind of almost give away immediately the answer to the first question by the second, because I ask here, wait a minute, why is this actually going to really be difficult to answer? Well, as we can probably see here, 126 ounces of paint seems pretty close to 128 ounces, but just what feels close isn't necessarily always the best measure of what is rare or not rare, right? I want to go ahead and admit to myself that I don't actually have much experience. So I'll say here, we don't have much experience with such a machine. And so we don't know if 126 ounces is rare, right? Like, I really don't know if that's rare. It seems a bit below average, but maybe that's still a typical amount, right? Not everybody is always average. So what we're looking for in this section is a way that we can go ahead and take this 126 and then we can start to assess its rarity. And to do that, we'll take a look at the topic of what we call Z-scores, which is listed down below. Now, in this box here, you'll see that a Z-score ultimately represents how many standard deviations a data value is from the mean. Okay, so we can see here that we can calculate a Z-score by just doing our individual X value minus an average, so like figure out how far away from average it is, and then divide by a standard deviation, or how many standard deviations go into making that distance. Now notice here that I have two different formulas, one for a population z-score and one for a sample z-score, but at the end of the day they ultimately are the same formula. I just notate my mean and standard deviation with slightly different symbols. So I'm going to go ahead here and take a look at the fact that in the numerator of these fractions I have a subtraction between two values, which of course then means that it's possible that if x is smaller than my average, I could get a negative number up top, and if x is larger than my average, I could get a positive number up top. So we'll say here that a positive z-score means that our data value x is larger than average, and a negative z-score would just be an indication that the data value we were looking at was below average. So let's go ahead and figure out how we could use this in something like part B. What if we know that this machine that dispenses paint has a standard deviation in the amount that it dispenses of about 0.48 ounces. Okay, so again, if I look back up here, 128 is average, but don't be too surprised if you get something about 0.48 more or less. Determine the z-score for the amount of paint in the can that we have. So notice, I would go ahead and I would fill in all the information that I have up here. X, that's the amount of paint in our can, which is our 126 ounces. We have an average amount of paint that the machine produces, which is 128, and the standard deviation we were just told is 0.48. Now, if I was to go to my calculator and actually crunch this out, you could see that if I rounded this value off to 4 decimal places, I end up with something like negative 4.1667. Okay, so again, what this means, if I was to interpret this, is that this means that 126 ounces is 4.116 standard deviations below average. That's all that this is really saying. The amount of paint that's in our can, our 126, is this many standard deviations, and the negative just indicates that it is below average. Okay, so the strange thing is this doesn't really tell me, though, if what I'm seeing is weird. And to get a general guideline for how we use z-scores to assess kind of weirdness or rarity, you can take a look at the box on the next page. So the guidelines that we have for evaluating the strength of evidence from z-scores. As I state here, z-scores give us this really quick and informal way of evaluating the likelihood or the rarity of our sample. In this case, our sample paint can. If I get a z-score that's somewhere from -1.5 to +1.5, I'm going to consider that X value not very rare. If I go a little bit beyond, it's moderate rarity. If I go above or below 2, so I start getting into the range of 2, I start to say that item becomes rare. And if I get like 3 standard deviations away, then I can say that what I saw was very rare. So notice that up above, we have a z-score of about -4.1667. That's definitely falling into this last category of a very strong rarity. In fact, I'm going to note up here that based on the table below, the can with 126 ounces is very rare. It may seem like, oh, 126, that's so close to the average of 128. But apparently not, because it's only kind of standard to deviate of about 0.48 ounces. So going 2 ounces away is actually a really big stretch. So I can use this to understand a little bit more about how I can use these scores to help measure rarity. The last observation that we'll make here in this video is that really whenever I have a data point that falls 2 or 3 or maybe even more standard deviations above or below average, that's considered to fall out into the tail of a distribution. So remember that we've often thought about having like nice bell-shaped distributions, and tails of distributions are kind of over on the side, where I happen to be, maybe 2 or more jumps away. This is where I ultimately hit a tail of a distribution, and I start to say that things become rare. I can have the same sort of behavior in a skewed left or a skewed right distribution. That still works the same way. But I've drawn a picture here of something with a symmetrical distribution. So what we'll see in the next video is how we can actually start to take a look at using z-scores not only to measure rarity, like we've seen here with being 2 or maybe 3 jumps, 3 standard deviations away from average, but that we can also use it as a way to help determine when things are not very rare by having a very low standard, a low z-score from the calculation that we've seen up above.